All right. Good morning, grade 12s, and welcome to Tuesday. Today, hopefully, yesterday went well and you had a good understanding of the topic covered yesterday. Um, the main idea yesterday was we were basically looking at non-linear graphs or non-linear functions and trying to estimate the kind of the average slope or average rate of change over a period of time. Okay. So again, I'm going to just sketch a little nonlinear function here, kind of show you the idea of what we are doing, right? So for example, maybe we are looking at, let's say, for example, we're looking at an exponential function. Okay. This is what an exponential function looks like, right? We notice that with an exponential function, or we know that with an exponential function, that the rate of change or the slope of that graph is constantly changing, right? At the very beginning, right over here, our slope is not very steep, or our slope is a very low number, close to zero. And as we progress, right, to different points on this graph, our function or our graph gets steeper and steeper, or our slopeness increases, or our rate of change is increasing. Okay, it's getting steeper and steeper. At no point on this graph are your slopes the same. Now they could be very, very close, very, very similar, but at no 2 points are your slopes the exact same. So we say that in a nonlinear function, most nonlinear functions, your slopes are changing, okay, or not the same. So what we did yesterday is we looked at, well, how do I, if I want information about the slope of a nonlinear function or the rate of change of a nonlinear function, how do I determine that? And what we did yesterday is we said, okay, well, let's say I want to know between the points x equal to 1 and x equal to 5, right? I want to know what is the rate of change, or what is the slope of the graph between these 2 points. Well, what we can do is we can estimate that, okay? We can do that by drawing what we called a secant line, okay? Now a secant line is a line that passes through 2 points of a graph. Okay, now that secant line there is not perfect, but the idea here is this line would pass through just these 2 points of the graph. And by drawing the secant line and finding the slope of the secant line, we can kind of get an estimate of what our slope of that section is. Okay, so yesterday what we did is we determined, well, this coordinate maybe is 1 and 2, and maybe this coordinate is 5 and 8. And what we did is we used our slope formula that you've been using for the past few years, which is y2 minus y1 over x2 minus x1. And we use that to determine the slope of what we call the secant line, right? This is a secant. Okay, so a secant, remember, passes through 2 points. Okay, we also wrote this as f of x2 minus f of x1 all over x2 minus x1. And all these things, f of x2, all that means is if I have an equation, I sub my x2 coordinate into my function, that would give me my y value, or my corresponding y value. The same for f of x1. That just means if I sub my x1 into my formula or my function, that's going to give me my y value, or my corresponding y value. Okay. So we calculated our slopes of our secant line that way yesterday, and that what that did is that tells us kind of our slope or rate of change of a certain interval on a non-linear function. Okay. Now the question becomes, like, because these rates are constantly changing, or our slopes or our rates are constantly changing, is what if I want to know the slope of the graph at a specific point, Okay. I don't want to know the average between 2 points, but I want to know at a specific point how steep is my function, or how steep is my graph, or what is the slope, or what is the rate of change at a particular point. And what that can do is that allows us to analyze different functions in different ways. Okay, being able to find that information. So today, what we're going to do is we're going to look at what's called the instantaneous rate of change. An instantaneous rate of change basically means at a particular instant, okay, at a particular instance, 1 point in time, what is the slope of a graph? So I'm just going to erase this here. So we have our secant, right? Now, if I'm looking at, let's see, I'm just going to erase some of this. Okay, so when we're talking about instantaneous rate of change, what we're looking at, let me draw my graph again, is at a specific point, what is my slope at this specific point? Okay, and I'm going to show you how to do that today. And again, because, and this is, we're going to be estimating it. Okay, so a tangent line. So yesterday we started with what is a secant line, and remember, a secant line is a line that touches or passes through 2 points. A tangent line, similar to a secant line, but a tangent line is a line that touches the graph at only 1 point, okay, within a small interval of the relation. It could, but it does not have to, cross the graph at another point outside of this interval. So a tangent line touches the graph at only 1 point. So for example, I'll go over to my exponential function here, and a tangent line would basically be drawn like this. It would basically go through, and it's only going to touch our graph at that 1 point. Okay, so this is what we call a tangent line. A secant line, remember, touches the graph at 2 points. A tangent line touches at just 1 point. Now, there could be cases, and I'll draw you a quick example here, but there could be cases where maybe a tangent line is going to go through a graph or touch a graph at 2 points. For example, if I did maybe a secant line, or sorry, a tangent line right here, right, that touches just this point, my tangent line might look something like this, right? That tangent line there is also going to connect with the graph over here, but we're focused on just the fact that we're focused on just this point here. So sometimes a tangent line could pass through at 2 points, but in general, we're looking at just that one specific point that we're focusing on. The tangent line goes in the same direction as the relation at the point, okay, which is we refer to as the tangency. So if the graph is traveling downwards, right, or it's decreasing, our tangent line is going to be decreasing. If our graph is increasing, our tangent line is going to be increasing. So the instantaneous rate of change, which is what we're interested about today, is the exact rate of change of a function at a specific value of the independent variable. So we're looking specifically at a particular x coordinate, and we're trying to determine the instantaneous rate of change there. And in order to do that, what we do is we determine the slope of the tangent. So the tangent line that I drew here, this orange line, if I'm able to determine the slope of this line, that will tell me the slope or the rate of change at that particular point on our function. Okay? So, and I'll read this again. The slope of the tangent at a point on the graph is equivalent to the instantaneous rate of change of the function at that point. Okay, so in order to find our instantaneous rate of change, we need to find the slope of the tangent line. Now, for short, yesterday we wrote for average rate of change, we wrote AROC or AROC. For instantaneous rate of change, for short, we're going to use IROC or IROC. So the slope of the tangent cannot be calculated directly using a formula or using the slope formula because the coordinate of only 1 point is known, right? For us to determine using our slope formula, remember our slope formula is y2 minus y1 over x2 minus x1, right? We need two coordinates to do that, to use that formula. Because a tangent line passes through the function or through the graph at only 1 point, we only have 1 point to work with. So we can't really use or directly use our slope formula. The slope, however, can be estimated. Okay, and I'm going to show you how to estimate that. By calculating the slopes of secant lines that go through the fixed point of tangency and points that get closer and closer and closer to the fixed point. So the idea here, and I'm going to zoom in on this here in just a moment, but if we look at this graph here, now it's a little blurry, but our function in this graph is our blue function here, okay, our blue line, our blue curve. And in this graph, what we're doing here, what you can see being done is here's the point, our point of focus is right here. This is the point that we want to know the slope of, or we want to know the rate of change of. So what I can do is if I do a secant line from our point P over to this Q value here, right? And then I draw another secant line that's maybe at a point closer to the actual point of interest. So maybe this secant line here. And then maybe I pick another point closer to my point P. So notice how I'm getting closer, right? I draw another secant line. Notice that as I pick points Q that are closer and closer and closer on the graph to point P, my secant line becomes closer and closer to the actual slope of the graph at that point. So the idea is what we want to do is we want to pick a point that is really, really, really close to the point that I want to focus on. So it says here, the slope of the tangent at a point on the graph is equivalent to the instantaneous rate of change of the function at this point. So it says choosing, I don't know why that's, let me just see if I can change that. Choosing a point Q closer to point P allows for a better approximation of the slope of the tangent line, which is equal to the instantaneous rate of change. So what we're going to do is we're going to go through an example where I'm going to choose multiple points closer and closer and closer to my focus point, which is what I want to find the rate of change of. So the relationship between slope of secants and the slope of tangent. So as point P is chosen closer and closer to as point Q is chosen closer and closer to point P, the slope of the secant line, PQ, becomes progressively a better estimate of the slope of the tangent line at P, which is equivalent to the instantaneous rate of change of P. So in order, what we're going to do is we're going to use this function as an example. Okay. So this graph, it says, estimate the instantaneous rate of change at x equal to 2 for the function f at x equals 5x squared minus 7 by completing this table. So I'll give you a second to just copy this table out here in your notes. And I'm just going to go through and determine each of these values. So in each of, on the left-hand side here, where it says preceding interval, basically what we're doing here is we're calculating the AROC, which is what we did yesterday. We're calculating the average rate of change between the x coordinates 1 and 2, and then 1.5 and 2, and then 1.9 and 2, and then 1.99 and 2. And we're going to see what happens as we get. Notice how my interval is getting smaller and smaller and smaller. The gap between those 2 points is getting, P and Q, is getting smaller and smaller and smaller. Closer and closer and closer to the number 2. Okay? So, let's see. So 1... All right. So what we're going to do here, so this is how I calculate. So change in f of x over change in x. All right. So it's just what it's doing here is we're calculating this. Now I'm going to show you how we get these numbers here. So 13 minus negative 2. The idea here is, in order to get these numbers, this 13 comes from, this is 1 squared 5. So this is 1, this is 5 bracket 1 squared minus 7, and 5 bracket 2 squared minus 7. So that's 4, that's 20. Sorry, so these two numbers are basically by subbing in. I get these two numbers by substituting in my x values into the equation. Okay, let me actually write this out a little better here. I apologize for this. So let's go here. We'll go, the negative 2 here comes from subbing in. So this is 5 times 1 squared minus 7, right? So that's equal to negative 2. And the 13 here is from subbing in 2. So 5 bracket 2 squared minus 7 is equal to 13. Okay, so a change in f of x, remember that's just my y2 minus my y1, and change in x is just my x2 minus my x1. So we're just subbing those values in. Okay, and then that's how we calculate our average rate of change, by doing the change in f of x divided by the change in x. Okay, so these values are calculated here for you. Now, if I were to sub in, so again, we know what happens if I sub in 2. If I sub in 2, I get 13. Minus, if I sub in 1.9, I'm gonna write this out. So if I sub in, actually let's write it like this, 13 minus, I'm going to sub in 1.9 into my equation. So that's 5 bracket 1.9 squared minus 7. That becomes, that's 13 minus, sorry, just give me 1 second to write this out. 5 bracket 1.9 squared. I just have my answers written out, which is not good. Is 11.05, which is equal to, if I subtract those values, I get 1.95. Okay, and if I just do 2 by, I get 0.1. Okay, and this, if I divide 1.95 divided by 0.1, I get 19.5. Okay, now if I do this again, if I sub in 1.99 into my equation, I get, so if I go this, I get equals, I'll write this out, so this would be 13 minus 12.8, which is equal to 0.2. And if I go, here I go 2 minus 1.99, that's equal to 0.01. And I divide these, 0.2 divided by 0.01, and I get, that would be 20. Okay, so notice here, and I think my estimate was off slightly. Oh, no, that's right. Oh, 0.005. But notice what's happening here is we're getting our values. So we were at 15, then we were at 17.5, then we were at 19.5. The gap is getting smaller and smaller between my average rates of change. Okay, so as you pick two x values that are closer and closer together, what you're doing is you're making a better estimate for your average, your instantaneous rate of change. Okay, now what we're going to do, so that's from the left side. Okay, so these are from 1 to 2, 1.5 to 2, so from the left side. Now what we're going to do is we're going to approach it from the right side, so numbers bigger than 2, and we're going to get closer and closer to 2. So if I do that from this side, my values, entering these into my calculator, Okay. Here I would get a leg at 11.25. If I sub in 2.1 into my equation, my y values would give me, my change in y values would be 2.05. Actually, what I'm going to do, I'm just going to pause here for a second. Okay, just because I'll show you how I get these values. So these two here are my y values if I sub in 2 and 3 into my equation. Remember, my equation was 5 bracket 2 minus 7. That's equal to 13, so that's my y1. And if I sub in 3 into my equation, 5 bracket 3 squared minus 7, that's equal to 38. So that's where I get those two values from. Okay, my y2 and my y1. So y2 minus y1, x2 minus x1. Okay, and if I continue to do that, so here I get a slope of my average rate of change between 2 and 3 is 25. My average rate of change between 2 and 2.5 is 22.5. Notice what's happening here. We're getting closer and closer to 20. If I sub in for the x coordinates 2 and 2.1, I get a change of f in f of x at 2.05. I get a change in x of 0.1, right? From 2 to 2.1 is just a change of 0.1. And if I divide these two values, 2.05 divided by 0.1, I get 20.5. Calculating again, making my points even, my x coordinates even closer, or my interval even closer. If I determine my change in f of x, I get 0.2005. My change in x is 0.01. And if I divide these two values, 0.2005 divided by 0.01, I get 20.05. Okay? So noticing here that as I get closer, my rate of change is getting closer and closer to 20. Okay? So based on the trend in the average rate of change, the instantaneous rate of change when x is equal to 2 is going to be approximately 20. Okay? It's an estimate, but we notice that from both sides, we're getting closer and closer and closer to 20. I'm just going to pause this video for just a moment, and then I'll continue.